press the bell icon on the YouTube app and never miss another update.
Hello children, our discussion of atomic structure continues. This is 8th part. So let me revive the discussion what we did so far. So I mentioned out that electromagnetic spectrum is the arrangement of radiations. Spectrum is the arrangement of radiations on the basis of their increasing wavelengths. Electromagnetic radiations are produced by a charged body. When any substance is heated, it produces electromagnetic radiations. One or the other way, almost all electromagnetic radiations will be produced when any substance, any body is heated out. Light is also comprised of electromagnetic radiations, means light which comes from the sun, even cosmic rays, the light which comes from sun, it also is composed of cosmic rays, X-rays, then you have gamma rays, then we all know we have ultraviolet region, then you have infrared, we have visible region, you have infrared region, then you have got radio waves, microwaves, so on and so forth. Almost all types of portions are present in sun also. But cosmic rays do not get a chance to come out from the nuclear core of the sun itself, because there is conversion of those cosmic rays into some other radiation that occurs in the sun. Sometimes at certain places, if you see, which is solar flares, these solar flares are made up of cosmic rays, and anything they fall on, these will be able to cut those into pieces itself, because extreme high energy radiation these cosmic rays are. But the light that reaches to the surface of earth, as I said, this light also is a type of electromagnetic radiation itself, because anything, children, any substance, when it is charged, when it is heated out, atoms, molecules are, and when they are heated out, they are actually charges. So the electric and magnetic fields, the oscillating electric and magnetic fields, mutually perpendicular to each other in electromagnetic radiations. So heating a substance will let it to produce electromagnetic radiations. All types of radiation will be produced. Some will be more, some will be less. What we mean to say is, electromagnetic radiations are composed of wavelengths. Correct? Some wavelengths produced are more and some will be less. So is it clear? So light also has electromagnetic spectrum, and electromagnetic radiations, as I mentioned yesterday clearly, are the radiations in which electric and magnetic fields are mutually perpendicular to each other. The speed of all the electromagnetic radiations in vacuum is same, irrespective of the wavelengths. The speed is same, that is 3 × 10⁸ meters per second. Then one more important thing what I told you, like matter waves, we have sound waves and we have water waves, they don't need medium for traversing. In vacuum they will also travel, they can travel in the vacuum as well. Today we continue the discussion of dual nature of matter, and in that, as I mentioned earlier, we will show by experimentation that indeed light also shows dual nature. Not only matter, a general matter, light actually is also a type of, is a matter only, so it also shows dual nature in it. Some of the phenomena, children, if you look on some of the phenomena shown by light, like what? Like diffraction. What does diffraction mean? Diffraction means bending of light. Now bending of light, if you want to see, suppose this is an object and you are passing light into it, you will see on the back of it there will be some light present as well. So this light bends around a particular substance. That can be explained by wave nature. So in our second year, we'll be reading about the diffraction phenomena, how exactly it happens. And maybe you have read it already as well, children. If you have a bit of concept with respect to diffraction, you know there are fronts generated, the fringes generated by the light, and there is overcoming of the different regions of the light, which produces light in the regions where actually light is not reaching. That is due to the bending property of the light itself, a general wave. There is one more phenomena like interference. Interference means merging of two lights, merging of two waves. I'll talk about wave here rather than light. Merging of two waves. When the two waves will merge with each other, say we have this crust and trough, then we have one more wave with crust and trough. When the two merge into each other, the resultant amplitude of the wave increases. This can be explained by wave nature of electromagnetic radiations, and in the present case we are discussing about light. So light undergoes interference. That means the waves can do constructive interference, in which two crusts will merge with each other and result in the higher amplitude, or one crust will fall in one trough, it will lead to decreased amplitude. This can be explained by the wave nature of light, by the wave nature of electromagnetic, or by the wave nature of a particular wave. Is it clear? However, there were many other things exhibited by light or exhibited by electromagnetic radiations, electromagnetic waves to be precise, which could not be explained according to the wave nature. Like the concept of black body radiations, photoelectric effect, specific heats of solids on heating, that is on increasing temperature. These are certain phenomena that could not be explained taking into account only wave nature of electromagnetic radiations. This had to be explained by some other phenomena which comes out of the wave nature of electromagnetic radiation. So children, we are now reading two important experiments, that is black body radiation and photoelectric effect, in order to understand the light or electromagnetic waves do contain particle nature as well. First of all, every one of you should understand one important thing. What is that? That electromagnetic spectrum is comprised of various frequencies and various wavelengths. Some of the frequencies are produced more, some of the frequencies are produced less, but it contains all the frequencies in it. I have given you the increased order of the wavelengths with respect to the electromagnetic spectrum yesterday, and as I mentioned out, that light is also comprised of, light itself is an electromagnetic wave, electromagnetic radiation. Clear? Now, first one, the concept of black body radiations or black bodies. Try to get this thing clear first of all. Say children, we have any substance. When incident light comes on it, there are three things that happen. One, some of the waves get reflected. Here I will talk about light. So some of the light gets reflected. Some of it is transmitted. And some of it is radiated. Now, whenever light comes on this source, on this substance, the color of this substance will depend upon what is the wavelength that has been reflected. If you are able to see a particular color of some substance, that color is on the basis of the reflected wave that has reached your eyes. If you are able to see something red, when the white light falls on it, rest of the colors may be absorbed. The wavelength that is coming back to you is red. Remember, it is not only the red wave that is coming and getting reflected, but the intensity of that red wave. What does intensity mean? Intensity means the brightness in simple terms. So intensity of that red wave out of all the waves is more. So you are able to see particular color. Clear? Now some of it is transmitted. What does transmission mean? So as the incident rays falls on this, after passing through this sample, after passing through this body, some of it is passed through, it's transmitted. And some of it is radiated. Exactly, it means incident light. After it comes, it's absorbed after certain time, after regular fixed intervals of time, it is being radiated. Is it clear? So, if you have a body, if you have a substance which is able to absorb all the radiation and able to emit all radiation, such substance, such body is called as black body. And the radiation is absorbed or emitted is called as black body radiation. So in simple terms, children, an ideal black body will absorb and emit all the radiations. Now this, what does it explain to us? How does it explain the particle nature of light here? How does it explain the particle nature of the wave here? Have a look on this, children. If you see some iron rod, it's a basic example that's in our textbook as well. If you see iron rod and heat it, first of all it will be dull red. What do I mean to say by dull red? That means the wavelengths which are coming to you, there are many wavelengths coming to you, but the intensity of the red wavelength is more. So you are able to perceive that more. Are you getting it or not? So if the intensity of the red increases, what does it mean? It means the amount of energy? No, it means the amount of that light reaching your eyes is more. Is it clear? Many wavelengths will be coming out of it, but the one which is visible to you will determine which wavelength is predominantly coming out of it. Is it clear? Now, after you further heat it, when you are further heating it, as I mentioned our children, any substance, when it is heated, it will start to produce electromagnetic waves of varying wavelengths. What color of that substance will appear to you will depend upon, out of these wavelengths, whose intensity is maximum. So if a substance is able to absorb all the radiation which are given to it, what will be the color of that substance? Perfectly black. So, or if it's able to emit all types of radiations out to you without any changes in the intensities of different wavelengths, then the color will not come to you at all, because there are multiple things coming to you. And what we are able to see is the visible zone. And we know, children, the combination of the 7 colors which you are obtaining on dispersion. I told you yesterday, when white light is passed through the prism, it breaks into how many colors? 7 colors. When those 7 radiations are coming to you with same intensity, the color will be merged out, and the net color that comes out to you will be white. It will not be bifurcated into any color. You cannot observe any color itself at all. Is it clear? Good. So dull red. After you further heat it, now understand it, after you further heat it, you will find out it converts to deep red, it converts to red. Means now you will be able to see full red of it. Then further, if it is heated, if you keep heating it, this converts to white. That means earlier what was the maximum wavelength reaching your eyes? Red. Now what is the maximum wavelength reaching your eyes? All are reaching your eyes now. All the wavelengths are reaching your eyes. So color changes to white. And then further heating it converts its color to blue. So on increasing the temperature, you got dull red, then you got more red, then you have white, and then you got blue color. So you see that in VIPGAIAR yesterday I told you what, that violet has got less frequency and red has got, violet has got less wavelength and red has got more wavelength. That means on increasing the temperature of a particular substance, what's happening is that it is emitting the radiations with decreased wavelengths, means the frequencies are increasing. So increasing the temperature, when you are increasing the temperature, the wavelengths are regularly what? Decreasing, energy is increasing. I'll just plot one graph here with respect to intensity and wavelength at varying temperatures. I said when you are increasing the temperature, the energy of the wave which is reaching you is increasing or not? Yes. That means frequency is increasing, but wavelength is decreasing. Let us plot the graph with respect to this, children. Have a look. So this is our wavelength and this is intensity. When you plot the graph, initially the graph looks like this, children. But see here, the graph does not approach zero here. Let me tell you why. Wavelength is increasing. This is suppose temperature 1. Have a look. Now this is intensity. You can see that when the wavelength is increasing at particular temperature, this substance is emitting all the radiations. You see the radiations with high wavelength are very less. The radiations with very low length are also very less. But there will be one wavelength which is called as lambda max, at which the intensity of that color will be maximum. So a particular wavelength, at particular wavelength, intensity is maximum, and the color of that substance will be the same at which lambda max we have, at which, because after that you can see what's happening, temperature is same, right? What's happening? After some particular time, lambda is decreasing. That means, children, some of the radiations with extremely, at a particular temperature, at extremely low wavelength are less, at extremely more wavelength are also less, but you have one region where intensity is maximum. This will be the color of that substance. What if we increase the temperature? I proved it a while earlier. So what I am doing, if I am increasing temperature, what is happening to the intensity of the color? It is increasing or not? What is happening to the frequency? It is increasing or not? What's happening to wavelength? It is decreasing. Let us see. When we are increasing the temp, means now we are keeping a different temperature, that is T2, such that T2 is more than T1. You will find out the graph looks like this. Now this will be lambda max. I'll call it 2, this I'll call it 1, and intensity here. Have a look, children. Now tell me, if you take this wavelength into consideration, have a look, this wavelength intensity, at the same wavelength intensity is more or not? Yes or no? That means at higher temperature, the intensity of that particular wavelength or the intensity of that particular color technically means the frequency and the wavelength will be altered. So here wavelength will be, I'll call it I1, I'll call this as I2. So at lambda 1, what do you have? I1 and I2. I1 is less than I2. Higher the temperature, higher the intensity, higher will be the frequency, higher will be the energy, and lesser will be the wavelength. So at higher temperature, and at the same wavelength, the intensity of the color is varying. How can this come to you? According to classical theory, which was initially put forward, children, it was considered that electromagnetic waves are moving like this. Suppose if this electromagnetic wave has a frequency of 500 hertz, this whole wave will have the frequency of 500 hertz respectively. But we have seen altering the temperature alters the intensity. So color changes, the wavelengths are changing. That can only happen when the wave, electromagnetic wave, which is coming to you does not travel continuously, rather travels discontinuously. And Planck was the first who analyzed the practical results with his observation and said that indeed there is the moment of electromagnetic radiations coming into play, and each wave is composed of small packets of energy, which he called as quantum. What did he call it as? Quantum. And the same quantum, when we are talking about light, children, is called as photon. And what else he mentioned? He said that the energy of each quantum is directly proportional to frequency. In order to equate energy and frequency, he put the equation forward: E equals to h nu. Quantum is one discrete packet of the energy of that wave, while as quanta is n number of quantum. So in simple words, quanta is the plural form of quantum. Am I clear here or not? So if the color you are observing is varying, that means the particles which are coming towards you per unit time are more, but each particle will have same energy. This, if it is in terms of wave, then it should not have happened at all. It means that electromagnetic radiations are not moving continuously, rather they move discontinuously in the form of small packets of energy, which is called as quantum, and in terms of light, that's called as photon. And we also wrote yesterday, if you remember it clearly, children. So E equals to h nu for a photon also. Am I clear or not? So intensity keeps on changing by the increase of the temperature, wavelengths are decreasing, that high energy particles are produced. This explains the discrete quantized energy present in a wave, indicating it has got what nature? Particle nature. Are you getting the point clear here or not? Yes? Excellent. So what exactly are black bodies? Black bodies are the substance, or these are the bodies which absorb and emit all types of radiations. And technically, when you keep increasing the temperature of a particular substance, it keeps radiating electromagnetic radiation, because if you increase the temperature of any substance, there will be the oscillations of the charges present in that matter. As a result of that, electromagnetic radiations are produced. So remember that even light itself is an electromagnetic radiation. Clear or not? In which some of the radiations which are coming to you are more and some are less. Because I said light is also composed of radio waves, then microwaves, then ultraviolet, infrared. We know only ultraviolet, visible zone and infrared, but all other parts are also present, but they are less significant there, means amount coming out is less. However, increasing temperature can make a substance radiate radiations at varying intensities. Am I clear or not? So what exactly does black body mean? And how does black body explain to you the particle nature of the electromagnetic waves? Very simple, because you are able to see different colors are coming to play, because a substance cannot radiate any amount of energy, rather it releases the energy in terms of fixed quanta, and the energy of that quanta is directly proportional to frequency, which mathematically we did yesterday also. So E equals to h, what is nu equal to? We have done it yesterday, children. What is lambda equal to? C by V. What is frequency equal to? C by lambda. Yes, we did one more equation, E equals to h c into wave number. So this is how you can find out. So for 1 mole, if you want to find out, into Avogadro's number. Hope I am clear with the statement here. So black body radiation explains what nature? Particle nature of electromagnetic waves. And here we have a special reference with respect to light. Is it clear? Excellent. So one more experiment which also could not be explained by classical wave theory like black body radiations is photoelectric effect. Now, what exactly photoelectric effect is? Basic definition of photoelectric effect is emission of electrons from the metal surfaces by use of photons, that is light. And the electrons emitted out are called as photoelectrons. Photoelectric effect is a phenomena of ejection of electrons from the surface of the metals when they are radiated by light. As I mentioned out, light also does not travel continuously because light also has what nature? Particle nature, and that particle nature can be understood by the individual photons itself. So light is itself composed of what? Photons, right or not? And as I mentioned a while earlier in black body radiations, the energy of each quanta is how much? H nu. So the amount of energy that can come out from an electromagnetic radiation at a time can be H nu or n number of H nu. It cannot be 1.5, it cannot be 2.5, it has to be always an integral number of 1, 2, 3, 4, 5, so on and so forth. Am I clear? Good. So emission of electrons from the surface of the metal using photons, that is light, is photoelectric effect. How was this experiment conducted by Hertz? He conducted this experiment by taking a vacuum. Understand it, I'll explain the full-fledged phenomena with respect to this photo emission. Now he took a chamber, a vacuum chamber which does not contain any air. What for it was done, I'll explain that as well, children. And a metal surface. This is a metal surface. So this is a metal. In front of it one detector was kept, which was attached to an ammeter and then connected with a battery. So first thing, the vacuum that was put here was for the purpose when it will be radiated by light, if any electron is coming out of it, there should be no disturbances offered to the electron by the air present in between. So a vacuum surface was kept. Number 2, attach it to the ammeter and detector. This is detector. Which counts electrons and their kinetic energies. Means with what kinetic energy they have come out, with what energy they have come out. It will show whether current has come out or not, because when the deflections will come into play. So when this metal surface was radiated by light, expected result was electron will be ejected, and once electron is ejected, it will be taken up by the detector and counted its kinetic energy as well, and then deflections will come into play, and we'll see that, and we will have a clearance that light has been able to cause the emission of electron from the surface. So the use of light to emit electrons is photoelectric effect, and the number of electrons ejected out are called as and the electrons ejected out are called as photoelectrons. There are many other things that we need to understand here, children. So I've given a basic way how they devise an experiment to do it. We already know light does not travel continuously, rather travels discontinuously. Sir, how does it prove that it has a particle nature? How does it prove the particle nature of light? Indeed, if this light is acting only as a wave, how does this experiment prove the particle nature of light? If this acts only as a wave, then the removal of electron from the surface of metal is not possible. Because when it is only wave hitting the particle, the momentum cannot be transferred, the energy cannot be transferred from wave into a particle. You are getting it or not? So as a result of that, ejection of electron becomes difficult. Because this light is made up of small fundamental discrete particles of energy called as photons. Each photon has some fixed energy depending upon the light you have used, depending upon the wavelength you have used. Are you getting it or not? Because when we use different wavelengths, obviously different energy will be associated with different wavelengths. And according to that, we can see whether ejection is possible or not. In order for the photoelectric effect to come into play, the radiations that you are giving, the light you are giving, should have a minimum frequency, which we call as technically, which is energy, should have a minimum frequency by which ejection of electron will be possible. That amount of frequency below which photoelectric effect cannot be observed or is not observed is called as threshold frequency. You cannot cause photo emission from a metal surface by using any amount of light. I will explain that in a logical and molecular part itself. So every metal surface has a threshold frequency. If you give energy below that threshold frequency, metal will not be able to lose electrons at all. Let me explain it. Light travels in the form of photons. So when the photon will hit the electron, and if the photon has the right energy, then that photon will be able to eject the electron. Clear or not? Now, if that photon has right energy and you are increasing the brightness, you are increasing the intensity, the number of photoelectrons ejected out will also increase. Am I clear or not? Am I clear? But the basic thing required is that the light you have used, the energy you have used, the photons you have used, or the frequency you have used should be above the threshold frequency. And the electron which will come out with some kinetic energy. Am I clear or not? Clear. So what are the fundamental things they found in the photoelectric effect? Number one, what is that? No time lag. No time lag in ejection of electrons. What it means? As soon as the right light, means the right energy light, is put on the metal surface, photoelectric emission is observed at the same time, because that is natural. What will happen? When the light of right energy will be given, it will hit the electron, and electron will be ejected out of atom very easily from the nuclear pulse itself. I'll explain that in diagrammatic manner children itself. I'm talking about the observations. Second, because the light photon will transfer its momentum to the electron and it will come out. Second one, increase in intensity increases the photo emission. So if you increase the intensity of that right light, the photo emission is also increased. And third important thing, what was that? Photoelectric effect is observed above threshold frequency. Right? What is that? We'll mention that as nu naught. That is threshold frequency for us. Technically, that is the amount of energy out of the given energy that has been used to eject the electron out. Is it clear? So, photoelectric effect is observed above threshold frequency. If you give the light or the energy whose frequency is below the threshold frequency, so nu, that is the given frequency, should be more than threshold frequency, only then photo emission is observed. You can observe photo emission only when the amount of energy given has got more energy compared to has more frequency compared to the threshold frequency. Is it clear? Let us understand this phenomena molecularly. How exactly does it happen? Have a look, children. So if we see here, we have got a metal surface. Alright, keep those things in mind. So first of all, you cannot bring photo emission into play unless and until you have the right kind of energy. Number one. Number two, if you have right energy and you are increasing its intensity, what does it mean? The number of photons hitting per unit time are increasing. Then the photo emission is also increased, right? Third important thing, there is no time lag. As soon as right energy is used, as soon as it hits the surface of the metal, ejection of electron comes into play. Clear? Read and understand these things one by one clearly. Okay, let's have a look here, children. What exactly will happen? Photo emission you understood, right? Experimental investigation is also done. Or did you get it out or not? Right. Now let us see molecularly how exactly it's working. So this is also the experiment proving what nature of electromagnetic waves or light particle nature. Have a look now. Now we have this as a shell and you got a nucleus here. The charge of the nucleus is Ze, Z we'll say, and you have electron here. Consider this as a valence shell. Okay. Nucleus will be holding this electron by binding energy or nuclear force or electrostatic force. We need definitely to break this interaction between nucleus and electron. It has to be broken. In order to break it, you have to give it some energy, means you have to work on it. You have to do some work. The amount of energy required to break the electrostatic interaction, electrostatic force or binding force between electron and nucleus is called as work function. What is that called as? Work function, represented by work function. So work function simply is the amount of energy, or it's the amount of work you have to do. That means the amount of energy you have to put in so that electron will be ejected out of the surface of the metal, out of the metal. So technically what you are doing is you have to ionize this atom, ionize this metal atom. Now very simple, if we have suppose lithium, then you have sodium, then you have, so you have lithium, you have sodium, then you have potassium. So in the valence shell, if you want to eject the electron, it is from n equals to 1, this is from, n equals to 2, this is from n equals to 3, this is from n equals to 4. Or because children, electronic configuration of lithium is 2s1, outermost electronic configuration I've talked about. In order to let the electron to be coming out of the atom, we need to give it energy. So if outermost electron, or if the electrons are close to the nucleus, the electron to be ejected, if it is close to the nucleus, then the nuclear force holding the electron will be more. So if n value in which the electron is to be ejected out, if it is close to the nucleus, then the amount of energy required to remove the electron will be more. So work function of lithium will be more than work function of, I'll write it here. That means what? Work function of lithium will be more than work function of sodium, which will be more than work function of potassium. And indeed, experimentally when you look on the work functions, work function means amount of energy required to break the nuclear force. It is almost 2.2, this is 2.3, and this is almost 2.4. Now if you look between children sodium and magnesium, now have a look. The basic electronic configuration and stability also decides its work function. Now if you look on sodium and magnesium, sodium value is how much? 2.3, and magnesium's value is almost 3.7. So when you move from left to right in the periodic table, outermost electronic configuration will be 3s1. Here it will be 3s2. And naturally, when you move within the alkali metals from left to right, alkali to alkaline earth metals, the size will decrease. The amount of nuclear force acting on the valence electron of magnesium and acting on the valence electron of sodium, there will be difference. Here it will be more compared to that of sodium. So removing of the electron from magnesium is difficult compared to sodium. That's why work function of magnesium will be more than that of sodium. You'll have more amount of work to be done in case of magnesium compared to sodium. Very simple now. How principal quantum number will decide your children? So when you move from top to bottom, what happens to n value? Increases. As n value is increasing, the distance of the nucleus and the electrons is also increasing. Because of that, what will happen? Removing of electron becomes easier or difficult? It becomes easier. Thus increasing n decreases work function. So we can write down work function is inversely proportional to n. And what does n mean? Principal quantum number. You have to make use of these integrated classes very properly, children. Am I clear? So this is all about quantum numbers only we are talking about here. At this principal quantum number we are talking about, right? Good. So work function. What does work function mean? It's an amount of energy required to remove the electron from the metal atom. Clear? Did you understand the values of work functions here? Yes. So if an electron is close to nucleus, work function will be more. That means whatever the photon you will be giving, now you are giving radiation, right? You are giving light composed of what? Photons. Now as the photon will hit it, I am giving the energy equal to h nu. First of all, out of this h nu, some of the energy will be required to break the nuclear force. What did we call that as? Work function. That's also energy. And we will mention that as h nu naught, because nu naught is the threshold frequency, and associated with that threshold frequency there will be some amount of energy required for this purpose, right? So you got h nu is the amount of energy you have given. Out of that, the amount of energy required, used to break the nuclear force for photo emission was h nu naught. Rest of the energy will eject the electron out, and this electron will come out with some kinetic energy which is equal to half of mv square. So mathematical Einstein's equation for photoelectric effect is when the energy, when the photon of right energy, when the light of right energy is put or is incident on the metal surface, and if that energy is right energy, means above the threshold frequency, the frequency is existing, then photo emission will occur and the electron will come out with some kinetic energy. So how much energy you have given, out of that, some of it will be used to break the nuclear force, and rest of the energy will be converted to kinetic energy. So mathematically, children, how will I write this photoelectric equation? Yes, mathematically, how will we write it? So we'll write down h nu equals to what? H nu naught plus half of mv square, or we can write down in simple terms h nu, instead of half of mv square we can write kinetic energy, you can change that at the end, h nu naught plus half of mv square. So the photon, the energy you have given has broken, so it's law of conservation of energy. How much energy you have given, some of it has been used to do some work and some of it has been converted to what? Kinetic energy. Now tell me, if the amount of energy you have given, that is h nu. So if h nu, naturally this energy is due to frequency. If nu is less than nu naught, naturally what will happen is the bond between, not the bond, electrostatic interaction between nucleus and electron will not be broken. When it is not broken, electron will not come out at all, right or not? So once electron doesn't come out, photo emission is not observed. So if you look on the surface of, say, potassium, and you are radiating this potassium by red light, even for longer duration of time, if you use red light, we know the frequency ranges of red light is from red, specifically red, it is from dull red. It is from almost 4.2 to 4.3 into 10 to the power 14 hertz. If you are putting it for longer duration of time on the surface of metal, you won't see any photoelectric effect coming into play in potassium, indicating that the amount of energy you have used, the frequency you have used is not above the threshold frequency. However, if you are using yellow light, dull yellow light, it is red and dull yellow light for photo emission, you will definitely find there is detection in the experiment that we have talked about a while earlier. Photo emission does occur. Are you getting the point or not? Means that yellow light has the right frequency. So threshold nu of yellow radiation is more than nu naught of potassium. Am I correct in saying it? Nu of yellow radiation, frequency of yellow radiation is more than the threshold frequency of potassium. But here I will say nu of red is less than nu naught of potassium. That's why photoelectric emission is not observed. And when you look on this carefully, children, yellow light has got the frequency zone of what? 5.2 to 5.3 into 10 to the power 14 hertz. But when you look on the work function of potassium, it is only 5 into 5.0 into 10 to the power 14 hertz. You can see that very easily here. It is only 4.2 to 4.3. It is 5. It is 5.2. So how much is used for emission, breaking the nuclear force? 5. How much is remaining? 0.2 to 0.3. That will be converted to what? Kinetic energy. So can I break it out here? So I will write 5 into 10 to the power 14 hertz will be used as the energy to break what force? Nuclear force. 0.2 into 10 to the power 14 will be converted to what? Kinetic energy. That's what mathematical equation tells you. How much energy you have given? How much you have given here? 5.2 into 10 to the power 14. How much is used? Frequency. It is frequency, right? So H value will be common to both. I'm not taking that into consideration. I'll take only frequency. How much is used? 5 into 10 to the power 14. What will be kinetic energy? 0.2 into 10 to the power 14 hertz will be kinetic energy for us. Joules will be the kinetic energy for us. Did you understand it or not? So children, if the nuclear force is more, then work function will be more. So can I say logically, any atom with more ionization energy will have more work function, and the work function is more. That means the ejected electron will come out with kinetic energy, which will be less. So mathematically, what's the equation we reach it with? Faster, tell me the equation. What is the mathematical equation of photoelectric effect? Faster, all of you. So equation is, children, h nu equals to h nu naught plus half of mv square. You can also write this as h nu minus h nu naught will be converted to what? Kinetic energy. Yes. So you can also write this equation as this one. Right, children? H nu. What is nu equal to? C by lambda. So C by lambda equals to H C by lambda naught, where C is the velocity of that electromagnetic radiation. Here we are talking about light, and lambda naught, it will be wavelength of lambda naught, wavelength at which photo emission has occurred. Yes, used, plus half of mv square. That will be kinetic energy. So transferring it here, what will be kinetic energy equal to? Hc 1 by lambda minus 1 by lambda naught. So with the help of this equation, you can calculate the kinetic energy of this. H is Planck's constant, C is speed of light. So this is Planck's constant, this is speed of light, which is 3 × 10⁸ meters per second. One more equation what you can get from it. You can calculate even the velocity of the ejected electron. How? Have a look on the equation. H nu minus H nu naught equals to half of mv square, correct? What will that imply, children? H into nu minus nu naught. So transfer 2 here into 2. So it implies 2h nu minus nu naught. Right, m will be transferred to the denomination by m equals to v. Because it's square, put root here, it will be root of that. So velocity of electron will be root of 2h nu minus nu naught divided by m, which can also be written as root of 2h nu. What is nu equal to? C by lambda minus C by lambda naught, so on and so forth. So that equation I have already told you. Right, children? With the help of this you can calculate velocity, you can calculate the mass of the moving particle. But mass of the particle is known because here we are talking about what? Ejected electron. Because half of mv square means velocity of the ejected electron, not anything else. Velocity of the ejected electron, m is the mass of electron. What's m? Mass of electron. So did you understand it, children, clearly? Now one question with respect to photoelectric effect we can solve. Metal surface or metal of potassium is radiated by violet and green radiations separately. The kinetic energy of ejected electron will be. The kinetic energy of ejected electron will be. We have options here. First one, kinetic energy of electron. I'm talking about electron. Kinetic energy of electron ejected by violet will be more than kinetic energy ejected by green. Second, kinetic energy of violet will be less of the electron I am talking about. Kinetic energy of the electron ejected by violet, I am assuming photoelectric effect is happening, is less than kinetic energy of green. Third option is kinetic energy of the electron ejected by violet equals to kinetic energy of ejected electron by green. And fourth one is kinetic energy of electron ejected out equals to half to that of kinetic energy to that of green. Okay, now understand this. The first thing is that we have been given potassium. Potassium is given to us, right? Metal given to us is potassium. So metal surface is same. So when we are radiating out, when we are giving the light, when we are giving the energy to the electron to be ejected out. So we are using two different radiations for this purpose. One is, in one time we are using violet and next time we are using green to eject the electron. This is for green to eject the electron. So in both cases electrons are ejected out. But the simple phenomena here will be that we know lambda of violet light is less compared to lambda of green. Yes, because when you look on VIB, GYOR, this is increasing wavelengths, correct? That means decreasing energy. That means decreasing frequency as well. So wavelength of violet is less than that of green. That means frequency of violet is more than frequency of green. That also means energy of violet will be more than energy of green. Now tell me, children, work function in this case will be same or different? Same. So we have work function is same for both because metal atom is same. Because work function is same, energy that is given by violet is more than that of green. Say I have given some amount of energy, out of which photoelectric effect is happening. The work function for both is same because energy of, I'll write it mathematically here, energy of violet is more than energy of which one? Green. Work function of the potassium when we are using violet light equals to work function of potassium when we are using green, because work function for both is same. So H nu equals to H nu naught plus half of mv square. H nu of violet is more than H nu of green because H nu is green. Or yes or no? Minus. What is H nu naught? Both of these are same. So here energy is more. Sum up. Suppose the value was 10. I have used 3. Here the value was 7. I have used 3. How much is remaining here? How much is remaining here? 7 minus 3. 4. 10 minus 3. 7. So here the kinetic energy will be more compared to that of green. So correct option will be kinetic energy of the ejected electron when you have used violet light is more than that of green, because work function for the metal atoms will be same. However, if the metal atoms are different, then obviously we have to see what is the amount of energy used for the ejection of electron and how much of the energy has been given. One more equation and one more question with respect to photoelectric effect we can solve, children. You understood the photoelectric effect clearly? Yes. One more numerical with respect to this. It's application numerical, so I'm just writing it out. Green wavelength in green zone of visible spectrum causes photoelectric effect. So we have a wavelength in the green zone which is causing photoelectric effect in lithium. Is causing photoelectric effect in lithium. Question number 1. Can violet be used to bring photoelectric effect? Number 2. Can yellow be used to bring? Now, if we are using a wavelength in the green zone of visible spectrum to cause photoelectric effect in lithium, so in lithium we are able to use which one? Green, means wavelength pertaining to the green color, we are able to cause photoelectric effect. So if I write VIBGYOR, that means if green is able to bring photoelectric effect in lithium, 100%, blue will also do, indigo will also do, violet will also do. Because these three are in the low wavelength zone. That means energy of blue, indigo and violet is more than green. So all of these can be used to bring photoelectric effect. Not only that, if you are using violet, then the kinetic energy of the ejected electron will be more, because the energy provided by violet radiation, means energy provided by the violet wavelength, will be more compared to that of green. So photoelectric effect comes into play by violet, definitely. And what will be the difference from that of green light? The difference will be in the kinetic energy. That means kinetic energy of ejected electron when you have used violet will be more compared to that of kinetic energy which has been there when green was used. Basic thing. So definitely can violet be used? Yes. And if you are asked the relationship of kinetic energy, you should say kinetic energy of the electron ejected by violet light will be more compared to that of green. Simple thing. Can yellow be used to bring the photoelectric effect? So Gy. So if you are moving forward only, then the violet will come. So it is increasing wavelength. That means decreasing energy. So if green is able to bring, that doesn't give me surety. Yellow will also be able to bring. But 100% these three can bring. These three cannot bring, because it cannot. You cannot say by surety. Yes, if threshold frequency is meeting, it can bring. But according to the question which is given to you, can yellow bring? Definitely not. Because if green is the limit, below it every other wave will be able to do that. Wavelength will be able to do that. But not yellow, orange and red. No, we cannot use yellow for the photo emission to occur at all. Because when I am using the highest limit of green, yellow cannot be used, because energy associated with yellow will be less. So if I increase the intensity of yellow 100, 200, 300 times also, I will never be able to bring photoelectric effect, because the frequency is not in the threshold zone itself. Clear or not? Black body radiation and photoelectric effect. These two experiments definitely prove the particle nature of electromagnetic radiations, and in the present case we have discussed with respect to light. So I repeat, light does have electromagnetic components in it, because at high temperatures, as you say, the oscillating electric and magnetic fields are there, which will produce the waves, which we call electromagnetic waves. And those electromagnetic waves, when they are arranged on the whole, different types of radiation, when they are arranged in terms of their increasing wavelengths, we are getting electromagnetic spectrum. Am I clear? So light also has got all the electromagnetic waves present in it, but the only thing is some are more, some are less. When I have drawn the graph with respect to intensity and wavelength at different temperatures, you understood that the body which has been heated up keeps on radiating radiations, and black bodies are those which absorb and emit all types of radiations. Absorption and emission of radiations does occur from different substances in discrete quantities, and those discrete quantities prove that we have particle nature of light and electromagnetic waves coming into play. Right? In general way, children, when we started the concept of dual nature of matter, all these things that we discussed from past 3-4 classes are pertaining to the dual nature of matter only. Am I clear? Clear with the thought? Excellent. So we will be having the discussion of some numericals after some in our next class, and we'll see you. Thank you.